Keynote, we are very pleased to welcome Dr. Chunhua Liao. He is a senior computer scientist in the Center for Applied Scientific Computing at Lawrence Livermore National Laboratory. His research focus has been compiler techniques for correctness, performance, and productivity of high-performance computing. He is the lead author of the ROSE compilers IST translation API, OpenMP implementations targeting CPUs and GPUs, and a range of source-to-source tools. So I will leave the room to Dr. Liao for his keynote presentation.
Hello, just mic check. Can you hear me?
Yes.
Okay. Thanks for the nice introduction. So my name is Chunhua Liao. I go by the name Liao. And today, I'm very happy to have this opportunity to talk about my work and actually a lot of other co-workers' work. We are building source-to-source tools for HPC at Livermore. Okay. Just rough agenda for today's talk. I will give a little bit of background, then briefly mention 3 example tools. And actually, building tools is just part of our work. We also have a range of supportive work. I really want to mention them. Finally, I will give you some takeaway messages. So before I get into the actual talk, I want to give you some big picture. And in terms of compilers, in my view, there are 2 types of compilers. We have traditional compilers. We also have source-to-source compilers. As you can see on this slide, both types of compilers, they share almost identical design and the internal components. So they both accept source code. They have front ends to parse the code. They have a mid end to do a set of program analysis, transformation, optimizations. Finally, they have a back end to convert their internal intermediate representation back to, in one case, machine code. In the case of source-to-source compilers, would be source code. So you may wonder why people want source-to-source. Well, because in between, mostly in this mid-end, you can apply a range of source-to-source and transformations. You can extract all kinds of interesting information from your source code. Compared to traditional compilers, there are at least 3 major benefits of using the source-to-source approach. The first one is very obvious because the output is source code, so it's very human readable. And you can actually do a lot of manual investigation, further modification to make the output even better. And also the third benefit is portability. And in HPC, we have hardware and coming and go every a few years. And for the machine code generation, quite often you have to change a lot. But if you invest your efforts and at the source code level, and most likely, your investigation can still be kept for the next generation of supercomputers or beyond. So that's why at Livermore, we are very interested in source-to-source compiler technologies. And on top of that, we are building a set of compiler-based tools for critical applications. So as you can see from this slide, the compiler framework we are building is called ROSE. And many people ask what ROSE means. It's actually just some kind of flower name, so nothing special. And it has multiple front ends, actually. It supports C, C++, Fortran, and other programming languages. The majority of the work is really about this internal representation or intermediate representation. It's a high-level abstract syntax tree format. It's very close to the original input source code. We have an almost 1-to-1 mapping between the ROSE AST nodes to the original source code constructs. So in that sense, we keep the templates, declaration, functions, and loop structures. We even keep source and code comments. So you can actually still preserve and see the comments in the AST. So the majority of our work is to build a set of program analysis transformation APIs on top of the AST. With those APIs, developers can actually write their own compiler-based tools, and we build a lot of tools ourselves. We have quite some users who are also building their own tools using our APIs. So after the AST, of course, we have this backend. We can generate the source code if that's what you want, or we can optionally call some backend compilers for you. So you can generate the executables. So in many cases, the tools you build using those, they just act like a regular compiler. You don't really see this kind of source level transformation, then hand over to the backend compiler. You just replace, let's say, your build system with a tool built on top of our compiler. Then you just compile and run it. Everything is transparent. So if you pay enough attention, you can also see actually our framework supports binary executable also. But I have not getting involved into that aspect of this support. The overall goal is really to support important applications at the Livermore Lab. And we want to improve the correctness of those applications, because some errors for some applications, they have a huge financial impact, like $500 million they are at stake. And also we want to improve the performance, of course. We have supercomputers at the Livermore Lab. We want to support our application teams to run their code faster. And also another big push is to improve the productivity, because getting high performance computing is just one of the goals. We also want to help application developers so they can quickly port their code, easily maintain their code. So from a high level point of view, there are two types of tools we are building. The first kind, they are analyzers. Those tools, they do not change your source code at all. Instead, they will just extract all kinds of interesting information and out of your source code and present the results to the users. Let's say we have visualization tools, and if you are familiar with the roofline model in HPC, we have a tool to calculate the arithmetic intensity. That's a main metric you use to calculate roofline models. We also have a set of analyzing tools which can detect or find all kinds of issues in your applications. The second type of tools we are building, and they are translators, and their purpose is include optimization, code modernization, and refactoring, and so on. And you can see a list of example translators we have built using those. So one thing we learned from our experience is that quite often, if we write a tool and we modify somewhere in some million line code bases, users won't be confident to just accept that huge pile of code. So instead, we use this patching method. We actually quite often generate patch files and representing the tool transformations. So, and the application team, they can actually manually investigate and check the patch files, so they can focus on the actual changes we propose, our tools propose to apply. Then after they are happy with the patches, they can apply the patches to their million line code bases and then confidently commit to their Git repositories. So as you can see, in one example on the right side, this is a translator, and we developed using the ROS compiler framework. it combine and source code analysis and transformations to create patches. Those patches will replace some unsafe function calls in your critical applications with some safer alternatives. So you don't have like an out-of-bound memory copy, and you won't forget the training and null character and after your copy. So now I want to mention several example and tools and in little bit of details. So the first tool I want to mention is this AST inliner tool, and we are building. So I think for this audience, most people should already familiar with the concept of inlining. So you have some code and calling some function like this swap function call. The inliner and the compilers can actually inline this function call, replace this function call with the function body of this function. So in the end, you have a big chunk of straight line and code without the overhead of function call. Many tools compilers, they can work better and without several layers of function calls. So it's a very fundamental optimization. And at Livermore right now, the application teams, they are using high-level abstractions more and more in order to improve the productivity of HPC. Many of those high-level abstractions, and in the end, they are actual function calls. And while they introduce, while they increase the productivity, but in the end, if you use more and more high-level abstractions, your code become less and less understandable, and for both application developers and also compilers. So that's why some application team came to us asking, well, you have this nice rules framework, can you replace those high-level abstractions with some simpler language constructs so they can easily understand what's going on. So let's say one concrete example. At Livermore, some coworkers developed this Raja programming layer. So Raja essentially is kind of C++ library interface in the simplest view. It separates 4 core elements of loop execution. For HPC, mostly we talk about the loop execution, but if you look carefully, you can separate the concerns, 4 different concerns and outs, and deal with them differently. So you have this execution template, and you have the execution policy for HPC for different and hardware devices, and Raja provides different execution policies. The simplest policy, of course, is a sequential policy. And on top of that, you can have the OpenMP CPU multi-threaded policy, or GPU policy, or CUDA policy, or vectorization execution policy, and many other combinations. So the third concern is the iteration space. There are different ways to iterate on the loop iteration space. And finally, the actual computation of the loop. That's a loop body. And here Raja uses lambda expressions to represent the actual execution. So in the end, users are writing an HPC code at Livermore and many other places using those kind of high-level abstractions. So they define an execution policy, execution range, then they call the template function call, and they may replace the execution policy and based on what the target platforms they are interested in, and finally they pass some lambda expression in the end to represent the body. So the thing that's, and of course the example here is very simple and clear, but once you get into real applications, the code using Raja, they will look very messy. So we are building the AST inliner to actually replace, let's say, template function calls with the actual template function body. And we actually go through the core chain of, let's say, template spatialization, and also replace the lambda expression, the body with its actual function body. So in the end, the outliner will generate nice, clean, and scientific computing code for users to easily understand what's going on for their code using high-level abstractions. And as you can see, this work is still in progress, and we are still dealing with very sophisticated, let's say, lambda and functor issues and template function issues in the AST. But internally, we have this internal algorithm with 4 major steps. Those steps quite often are also the 4 steps we use to build many other tools we are working on. So the first step is to do some eligibility check. So before we do any transformation, we want to check if the transformation will generate the correct result, will actually be feasible to do the transformation. So the second step is to actually do some AST normalization to really simplify the AST a little bit, so we can actually more easily apply the transformation we want. And the third step actually is the majority of the transformation in terms of inlining, and we write tools to actually copy the body of the function to be inlined and replace the original function call with the body, and also replace the variable references with actual arguments. So the final step is the post-processing step. So after the transformations, we do some cleaning up, we reduce some unused variables, labels, and we remove other things. So in the end, the code looks much cleaner to the users. Okay, so that's for the inliner. The next tool I want to mention is the AST outliner. So this is kind of even more interesting. So I think most people are familiar with inlining, maybe less familiar with outlining, but semantically, those two transformations, they are exactly reverse to each other. You may wonder why we are interested in outlining. And actually in HPC, outlining, in my view, is a enabler for many multi-threaded HPC execution. Let's say for an OpenMP implementation, quite often they have to outline the loop body, as you can see on this slide, for this OMP4 loop, and annotated with OMP part 4. Most OpenMP compilers, they will actually extract this loop into a separated function, and in the original place, and some OpenMP runtime library function calls will be inserted. One of them will be something like this, and parallel start. This runtime library call will start multiple threads to execute something, and actually something is provided by this pointer to this outlined function. So as you can see, the outlining transformation is the enabler for OpenMP implementation, targeting, and CPU threads. We actually also write the code generation for CUDA code. So we can generate the outlined and kernel in the format of CUDA code. So we can offload the loops to be executed on GPUs. So the last but not least application is to enable whole application auto-tuning. So I will briefly mention one example later on. So again, the internal algorithm of AST outliner is similar to many other tools we are building. And in this particular case, we apply quite some program analysis, let's say side effect analysis, liveness analysis. The whole point is to improve the quality of an outlining, because you want to, first of all, reduce the number of parameters, and you want to pass into or pass outside of the function. In terms of C programming languages, you do want to reduce the number of pointer dereferencing. So because those pointer dereferencings, they confuse users and compilers. From users' point of view, we have quite some parameters and command line options available. So users can run our tool with all those different command line options to tailor the behavior, the internal behavior of the outliner. For example, there are many ways to pass variables into the outliner function. You can pass them one by one, or you can package those variables into some arrays or data structures. So you just pass the array and the data structures instead. You can generate the outlined function in the same original source file, or you can separate those functions out into another source file. We also support not just the conventional way to call the outlined function. We also have this interface built on top of DL open. So you can call the outlined functions through this DL open interface. This enables dynamically loadable libraries. So your HPC applications, the execution and the binaries, they can be kept intact. But while it's being executed or maintained for whatever reason, you can replace the outlined functions implementation and inside of the dynamically loadable library. So this is extremely flexible and to enable, let's say, runtime adaptation or tuning. So I really want to show a little bit of detail for the program analysis we use to enable this kind of more effective program and the outlining transformation. As you can see, we have, some introduction. Okay, we have this scope analysis. We have liveness analysis. We have address taken analysis, and we have variable cloning and transformation. And so in the end, this is the difference between the traditional outlining algorithm and our outlining algorithm. So as you can see on the left side, this is some piece of outlined function generated using some classic algorithm. The first thing you should notice that there are roughly 8 parameters passed into this outlined function. On the other hand, this is the code generated by our outliner. We actually reduced the number of variables to be only 5, because we applied quite some program analysis to really figure out what variables should be really passed into this outlined function. So another big difference is that the classic algorithms, they use a lot of pointer dereferencing in their code, and especially inside of the loop. As you can see, all those red fonts and text variables, they are actually the pointer dereferencing. All those pointer dereferencing, they confuse users, confuse compilers or tools for further optimizations. And our outliner actually generates much cleaner code. So if you are familiar with stencil computation, you can easily identify this piece of loop body and looks exactly like the familiar stencil computation. All those nice variables and array variables. We don't say actually any pointer dereferencing because we use liveness analysis and the variable cloning to reduce the pointer dereferencing. So those kind of program analysis really improve the quality of outlining. So in the end, we of course have many application scenario for source-to-source outlining, but I want to mention this typical use case of the outliner to enable whole program auto-tuning. So in many cases, you have a long-lasting execution for some HPC applications. You don't really want to restart or optimize entirely. You want to focus on some hotspot first. So you can call the outliner to generate a set of kernel variants, and you use this DL open interface we provide. So you can actually put all of them into this dynamically loadable routine. You can use checkpointing, restarting, and to try different versions out. And you can hook up with some search engine to really guide your search, because there could be like thousands or 10,000s of versions. So in the end, you can really find the best performing versions of your important and scientific computing kernel. So we did some experiments quite some time ago, and we have some new results, but here's something we can talk about. We have achieved, let's say, 5.5 and speed up for some kernel. We applied this optimization. For the whole application, we achieved 1.76x speed up. Okay, the third tool I want to mention is even more interesting. So at Livermore, and we have quite some application teams. They had an MPI only code. And what I mean by MPI only, those codes did not use any multi-threaded and single unknown parallelism at all. So they wanted to port their code to OpenMP, Raja, but they noticed that, wow, they had quite some global variables floating around. So they had to manually deal with. So just 1 second. So they came to us again, say, can you guys develop a tool so the tool can essentially tighten up the scopes of all the variables in their large scale applications? Of course, this kind of requirement sounds easy and when you first heard about it, but we actually tried several versions of our tool, and in the end, we deliver some tool our users are happy with. So let's say the simplest case of moving some variable declarations to innermost possible scope, and you have the declaration scope, you have the intermediate scope, and you have the user scope. And we actually build this kind of scope tree internally in our tool. We can, of course, easily decide, well, in this simplest case, we can just move this int I to the user scope. And if you have multiple uses of this variable declaration, of course, you cannot move to the bottom, but instead, you can only move to the first user scope. That's the second case. Of course, in real code, there could be multiple branches in your scope tree. So when you want to move the variable declarations, you really have to figure out the live-in relation between or among the scopes at the same level. So in this case, we have the variable redefined before it's some RUs. There's no live-in information. You can safely move the variable declaration to the bottom of those two scopes. If you do have those kind of live-in relation between the scopes, then you cannot really move to the bottom scopes. You can only move to what we call the first branch node instead. So as you can see, we already have to rely on scope analysis, live list analysis to drive the transformation. That's not trivial for real applications at all. And later on, we realized that, of course, there are different lengths, different depths for the scope tree, of course. Once you move some variable to one level, it opens up some further opportunities for this variable, let's say this variable, to be moved down further. So we changed our implementation to use this work list-based iterative algorithm. So we repetitively find the movement opportunity and move them around, and until we reach the point that no further movements are possible. But we found that this version of tool is not efficient because we had to move things around a lot. So finally, we realized that we don't actually have to move variables for each iteration. We only need to find the final target innermost scopes for each variable declaration to be moved into. So after that, we can do all the variable and declaration movement in one last shot. So this is our final algorithm. And it's really just separates the program analysis from the transformation. So in the end, we delivered this tool to our application teams. So I can only say XY applications, and they are very happy with this kind of tool. And after that, they requested even more features from us. So I think that's the downside of doing some good job of developing tools. So you develop some features, the users just ask for more. So I think that's actually good. So I think that wraps up my first part of talk. The majority part of the talk about the tools, the compilers, and we are building. So for the final portion of my talk, I really want to talk some other supportive work. And I think I've been in this HPC field for 10 plus years. And whenever people ask what HPC stands for, I think the standard answer is high performance computing. But I think maybe that's not really I say in the field. So in my view, I think HPC really stands for highly painful computing for a lot of people, including myself. I think fundamentally, I think the success metric is, in my view, quite biased because right now we focus on flops, watts only, but we don't really calculate the human factor. So in the end, as I interact with application teams, sometimes I even wonder, do they really want to use some HPC machines at all? Because we change our platform every a few years, and some applications, they may actually run well, but still they are forced to port. So I think as a community, we should maybe think more about those human factor. We should really define some more holistic success metric for HPC. And quite often, I think I'm some kind of service provider for my users. I develop tools, but really the users, they want results from me. So I really have to think about the total time for the users to get the results they want. And I really have to think about the quality of my results. How the speed is not the entire picture. We have to consider about the correctness, accuracy, certainty, and lastly, I want for HPC and developers and researchers, we want our results easily accessible under all kinds of situations. So we should not force our users to go through a lot of paperwork and jump through a lot of hoops in order to use our, let's say, compilers, tools, program model, or any other resources. So I think I can blame others for all those issues I observed, or I can try to do my part because I'm also part of the problem, I have to admit. So that's why I'm investigating how I can improve the services I'm providing to my users, because I'm part of the HPC community. I'm developing tools to help them. So the first thing I'm looking at is really the benchmarking and support for many tools I'm using or developing. Because fundamentally, if you cannot measure things correctly, you cannot improve it. So that's why we are very obsessed with developing regression tests with both positive and negative test cases. For example, for data risk detection, we developed this data risk bench suite. Essentially, it's kind of regression tests with both positive and negative cases. With those kind of test suites, you can actually easily generate true positive, true negative, true positive, false negative, those kind of results, and calculate standardized metrics. So in the end, you can easily evaluate the entire community and state of the art for all the different tools and what kind of results each of them can generate, how they compare to each other using this apple to apple and comparison. And actually we used our database bench to do exactly that. We found quite some errors in the mainstream database detection tools, and we communicated the results with them, and we helped the community to build a better database detection tools. And we also help them to actually improve their development cycle. For example, this is one tool we are focusing on. So the Intel inspector combined with the Intel compiler across different versions. So the green cells means they pass the regression tests. The red cells means they fail. As you can see, and from different from one version to another, sometimes the tool still performs well, but in some cases, the new version is much worse than the previous release. But immediately, maybe some people reported the issue, and the next version they fixed more, but also they introduced some new issues. So I think with regression tests like this kind of database bench, people can do better job of making sure the release of new version of tools will only deliver better quality to the users. So the second thing is, as we build more and more tools, we realize, well, quite often the pain point is how to use the tools. It's just too many steps people have to go through to use our tools. And also we realize that not a single tool, not a single research group can solve all those challenges. And we have to find a way to combine those tools into some composable services. And we are actually exploring this idea using this risk detection service framework. We are building microservices on top of individual tools. On top of that, we build a meta service tools, which will compose the results from multiple microservices and respond to users' requests using standard APIs, standard JSON formats. So if you are familiar with the RESTful API, I think you can recognize those are standard methods. So we define the URL parameters. So users can submit requests for the data risk detection servers. So in the end, we actually deliver the combined results to the user. As you can see, this example JSON output for this input program, we found several databases. All the results are standardized using this data and JSON format. We pinpoint the read write access points and how each tools reports if it's true, false, or anything else, and what kind of policies we use to combine different tools. So this shows one recent results we got, and we used the database bench again to evaluate this kind of risk detection servers built on top of multiple tools. So we tried different aggregate policies. So in the end, and of course, the composed risk detection servers generates the best accuracy and the best F1 score, and out of all those options. So I think this proves the feasibility of composing different tools and present uniform standardized results to the user. And finally, we build the tools, and we feel like there are too many requests from our application team, so we cannot really do everything on our own. So we have to think about the training pipeline. We want to train summer students, train new members of our group more efficiently. So we are looking into this online sandbox terminal system, so people can easily access the development environment. They can actually read the training instructions, and also with only a browser, they can immediately access the training environment. So in the end, this is and some website we are building called Free Compiler Camp. On left panel, you have the traditional tutorial text and instructions. On the right hand, you have this online sandbox, live environment, everything installed. You don't have to apply accounts and get your token. You can immediately jump into the practice in real time. Okay, I think reaching my end of my talk, just some takeaway messages. So first of all, we are very interested in this source-to-source approach for HPC. We have built many tools. So if you want to know more, here's our websites. From a tool development point of view, we realize regression tests with both positive and negative tests. They are essential for driving our own development and also to communicate the progress. So many of our tools actually report issues for application teams, but we realize that we have to be careful, and because those software, they're just the developer's baby, so be careful. And finally, in terms of the HPC community and overall, I think we should think about we are the service provider, so we should provide better services to our users and to make HPC highly pleasant computing. So with that, I will end my talk. I'm open for any questions.
So thank you for this nice presentation. We have around 15 minutes for questions. So I see that there is already some questions on the chat. So as Emmanuel put in on the chat before the keynote speak, please, if you have questions, put them in the chat. I'll check the chat and I ask them for keynote speaker. So we have the first question, a comment, then a question. So I believe that your observation on including the human cost of HPC development as part of a success metric for HPC is very important. Do you have any thoughts on how to objectively evaluate and compare the usability of languages, APIs, and frameworks?
Okay. Yeah, and I think this goes back to this slide. And I think we still, the best metric I can think about is the entire end-to-end time to solution metric, because right now we only focusing on the actual execution time on the supercomputers. We overlook from the beginning to the end what human cycles are involved. So in my kind of extreme view, I really want to even measure how many thinking steps people have to go through in order to do something, how many keystrokes, how many mouse clicks, and even the cursor travel distance. I'm obsessed with that kind of details. And if we start to measure those kind of objective things, we can actually get to the bottom of how to improve the productivity of programming languages, APIs, or edit tools. So I don't have like the final answer, but I think as a community, we can start looking into those kind of things.
Thank you. And so there's another comment say, I have a question on the analysis shown on slide 21. So would you be okay to share your screen again so we all can see slide 21, and I think
Okay.
then we'll have the question.
Yeah, sure, of course.
Thank you.
Let's see, slide 21.
Yeah, that's what in
there's no analysis on 21. Is this the right number?
It's slide 19.
Okay, 19. Okay, is this one?
Right. So thanks. So this is Chen Ding from University of Rochester. I teach and do research in compilers and find your talk really interesting.
Thank you.
And also, I thank the organizers of this C3PO for this chance to join remotely. So in this analysis, I see the goal is to analyze the scope and bring together the definition of use. So
Yes.
The way it's shown is more hierarchical in the structure. I wonder, do you need flow analysis to deal with cyclic control flows? So if there is a loop, for example.
Yeah, this is a very good point. And we actually have to build the control flow in order to do our analysis. And I only show the scope tree view. We actually have the control flow view of the problem also. And on top of the control flow, we have this live list information. Because, and I only briefly mentioned this live list information. Actually, this information is built on top of the control flow. So those two kinds of graphs are used together to decide if we can move things and safely. So thanks for asking for that. But I only skipped that CFG control flow part just to make this a little bit easier to understand for some people.
Thank you. That makes perfect sense. Nice
thank you.
Live analysis.
Yeah. Mm-hmm.
Thank you. So we have another common question. I was curious whether you think that we can arrive at a representation that would allow different compilers to exchange analysis information.
Oh, wow. This is actually my favorite topic, but I have not talked about this in this set of slides. I'm again actually obsessed with that problem also myself. A few years ago, with some collaborator, Professor Xipeng Sen, we developed some knowledge-based approach to actually communicate the program analysis among different compilers. In that work, we use this ontology and OWL. We define the terminology of language constructs, program analysis. We encode the results, program analysis from LLVM compiler and ROS compiler. Then we combine the results into one single knowledge base. On top of the knowledge base, we build up quite some interesting optimizations, program analysis. And yeah, unfortunately, I did not mention that work here, but yeah, I'm very interested in that. If I get the funding, I will pursue more in that direction. I really want to, because fundamentally for many tools we are building, the bottleneck is not the transformation, but really the supportive program analysis. Not a single compiler, single tool, single group can address all the program analysis challenges for those tools. So we really have to combine the program analysis together. And this kind of data risk detection results, how to combine them. This is actually another attempt to combine program analysis from multiple sources. Even with conflicting results, we still want to combine them, just using different aggregation policies. We even assign weights to different tools because they have different accuracy. We can even have, let's say, directive specific weights, because different tools, they can do better or worse for different types of codes. So we can have this kind of very fine granularity and weights assigned to different tools, so we can have a better way to combine different tools compilers for different program analysis. I'm very happy somebody asked this, so thank you.
Okay, so we have two more questions. I will start with the last one, which is a small one. Can you give the bib info for your earlier paper on knowledge-based representation? That's a question from Chending.
Yeah, and let's see if I can find this online.
So I think if you can provide it in the chat box.
Oh, okay. Yeah, that's
it's okay. Because we have another question, which is really quite interesting. It might also may take some time just to answer it and speak a little bit about it. I think it will be our last question. Have you think applied the outlining feature for some kind of common sub-expression elimination in a way that when different sections of code do the same computation, they can be outlined and replaced by a call to the function?
Yeah, I think that's totally doable. Right now, the way we work on our tools really is like driven by our sponsors. We have quite some sponsors. They are interested in some capability, so we just meet the requirements with their money. If we have funding for that kind of like a common expression thing, we can definitely apply the outliner to that problem.
Mm-hmm. Okay. And so I have also a question on the move tool. So your users asked you a tool to be able to find where variables are initialized and to reduce the liveness of their variables to help for their parallelization.
Mm-hmm.
And actually, do they ask you, or do you think that also you can use this kind of techniques after reducing the liveness of the variables to actually try to point them on where they can insert like their pragmas, OMP pragmas or something like that?
Oh yeah, that's a large tool, and I only briefly showed it here. It's called the AutoPar. This is some tool which can actually automatically insert the OpenMP directives into sequential code.
Okay.
So yeah, we have so many tools. So I cannot mention all of them. And this AutoPar also built by myself, and it's being used to help Livermore application teams to find the opportunities they can insert OpenMP directives. So the nice thing for this tool is it's semantics aware. So it actually will leverage some kind of, and you can even say that's knowledge base to encode high-level abstractions, high-level semantics, so it can parallelize more loops than conventional approaches. So if you are interested in that, you can Google this AutoPar tool. So it's also being used by quite some teams.
Okay. Okay, thank you. Thank you very much.
My
So
pleasure.
I think we don't have any more questions, and the first paper session will start in 2 minutes.